Well, thank you very much for the invitation to come and speak here. And first of all, I should apologise. Of course, this is going to be in English. I don't think you'd particularly enjoy it if I spoke in French. So I think it's probably safer. It's probably safer that we do this in English. And I hope you'll forgive me for this. This talk is about something called seismic metamaterials, and you'll hear. I'm going to meetings now, and you so often see this phrase being thrown around like confetti. And Stefan asked me whether I would give a talk which was like a survey, so you could see what this was and then make up your own minds about it. This is joint work by quite a large group of people, and the ideas in it come from a different field. They may mainly come from physics, an area in electromagnetics and physics where people want to direct waves in different directions, steer waves down fibers, optical fibers, that minimize losses, to redirect things. And so the ideas in that subject have developed along the lines of, let's build structured crystals, artificial crystals. And if we can make artificial crystals, then we can design materials that have things like negative refractive index. Really quite strange materials can be designed in physics. Now, the question then naturally arises, elastic waves, it's another wave system, it's not electromagnetics, it's a slightly different system. But can you take the ideas from physics and move them into elastic waves? What success would you have? Does it work? What sort of ideas are they? That's what I really want to try and get across. So the challenge is, you'll be very familiar with the challenges, probably much more familiar than I am. You know, the challenges in elasticity are, particularly in the sort of area that you're working in, that we have very low frequencies and very long waves. There's a huge mismatch of soil and the building materials that you're actually using. How do you deal with seismic site effects? The fact that you might have a kind of bowl in which the waves are bouncing around, and you get resonances inside this layer of softer soil. In elasticity, the full elastic equations are no joke. You know, they're quite complicated. They've got pressure waves, shear waves, Rayleigh waves, Love waves. We've got anisotropy. We could have all sorts of effects in there which are not actually present in the electromagnetic problem. So although we're trying to take ideas from electromagnetism, it's not as simple as, oh, I like that idea, I'm going to take that idea and I'm going to put it in that subject. It doesn't quite work like that. And so I'm going to try, if time allows, and please do throw me off if I carry on talking too long. I realize that this is a trait that one develops over time. I'm going to talk a bit about seismic mode converters. So I'm going to tell you what they are and how they might work. And then I'm going to talk about elastic surface wave lenses. And then I'm finally going to talk about phononic crystals with very large stop bands. So these are ideas taken from physics, applied to elastic waves. So seismic mode conversion, what would we love to do? We'd love to put something on the top. I've just drawn a forest there, but maybe it might be a collection of buildings. We'd love to send a wave at this and then have a surface device of some sort. And that surface device, its job is to turn Rayleigh waves into bulk waves. That's what we want to achieve. And there's a group in Grenoble in ISTER, which is an earth sciences laboratory, who are studying. Unfortunately, people won't allow us to send Rayleigh waves into buildings. I'd love to, but for some reason, people won't do this. Well, rather kindly, the French government about 20 or 30 years ago planted some trees in beautiful straight lines, which have now all grown to the same height, which was very, very thoughtful and very filled with foresight. And anyway, this now means that Philippe Roux and his collaborators can now send Rayleigh waves at an arrangement of resonators on the surface. The resonances are not at the same frequencies of buildings, but nonetheless, one can start asking the question, what happens if you put resonators on the surface of the Earth? What happens if you arrange them periodically? Now, so that's what they do, and there's an A&R project called Métamatériaux, and there's a web page up there, and there are descriptions of their experiments and what they do there. The next thing you might do is you might take ideas, once again, from electromagnetism. So in electromagnetism, there are quite a lot of ideas where people naturally use lenses, and you try to make lenses so that, for instance, you fire a wave at your lens, and you want all of the signal to go to the very far end of the lens. It's called a Luneberg lens. There's another one called a Maxwell fisheye. They have various names, and they're very well developed. People make them, use them all over the place. Could you make those lenses on the surface of the Earth by mediating the soil? The way those lenses work is that they have an effective refractive index, or in fact the refractive index changes with position. So if we could play around with the soil by drilling holes, inserting concrete and so on, we could change the material properties of that soil. And if we did it in the correct way, we could make that mimic the lenses that people use in physics. And in physics, these are called gradient refractive index lenses, GRIN. And that's why I put gradient index lenses there. The final one is perhaps a bit more, probably something you might more expect. That is to build something that reflects the waves. Now, as you'll know better than me, if you want to build something that's going to reflect ground vibration, it better be very heavy and very big. But could we, could we arrange things so that the multiple scattering between the objects had the effect of building a shield? So instead of just putting down a huge lump of concrete, could we put down in a periodic or a regular arrangement a collection of objects such that when the waves enter them and they bounce between each other, the bouncing between each other has the effect of building a shield? That's called a phononic crystal. And so phononic crystals are very, very popular, or photonic crystals, which is the electromagnetic version, are very, very popular in electromagnetism. There's an entire field called photonic crystal devices. People use photonic crystals and what are called the stop bands to design filters and lots of other optical devices. Can you use the same ideas, but now in elasticity, to develop elastic devices? And if time allows, I'll talk about them too. They're really the three basic ideas that are knocking around at the moment, that people are talking about. So the first one, surface sub-wavelength resonators. So we want to take an elastic half space, and we want to put resonators on the top of it. We want to fire Rayleigh waves at them and see what happens. And so we do these computations. We take a source function. We do it in the time domain. Sometimes we do it in the frequency domain. It's a nice model problem. It's a very clean problem. We just take a half space, we put a row of resonators there, they're all the same height, and then we study them. What do we see? So if it was just a row which went on forever, you can see that there's a certain periodicity to it. So we don't model the whole row, we just model one in a periodic cell. When the wave goes over the cell, there's a phase shift in the wave. And so you can draw what's called a dispersion diagram, which tells you how the frequency of the wave is related to the phase shift. And this picture, if one's practiced in reading it, one sees that the straight lines, they correspond to compression, shear, and Rayleigh waves. And then the resonance is punched lines in this. Unfortunately, if all the resonators are pretty much the same height, you get very, very small, what are called stop bands. So there are very, very small regions of frequency where waves will basically bounce off that structure and won't propagate through it. So if they're all the same height, it turns out to be a bit useless because you can only design this device so that waves will not propagate through it for a very, very small band of frequencies. Now, ideally, you want a broadband system. You want something where you fire waves at it and it stops or diverts them for a very wide range of frequencies. Preferably, in your case, the lowest possible frequencies you can think of. Now, I realize I'm talking too long, so I suspect I'll jump to the actual device itself. So in order to get things which are broadband, what you do is you play with the height. So you make a wedge, and by playing with the height, this means that when the wave, as the wave of many frequencies enters this system, so for instance, when it goes from the short to the long, at particular places, it hits the local band gap and gets reflected. And that creates what one could think of as a rainbow, an elastic rainbow. What happens is that as waves propagate through, different frequencies get cut off at different places and reflected back in different ways. And so that provides a surface reflecting device. Perhaps more interestingly, when you go from high to low, you send in a Rayleigh wave, it enters this object. And then when it hits the situation where it should be cut off, instead of being reflected back, it goes and reflects into the bulk. So in that case, you've built a device which, as far as someone standing on the surface is concerned, has no reflection and no transmission. So you can build devices which do sort of clever things, using the fact that you've got surface resonators. And in fact, it might be a bit brave. I might try and see. I'm not that brave. So you can actually analyze this. You can do it mathematically. You can figure out why the waves go in different directions. The picture just here shows the wave coming in, being reflected down on the one on the bottom, the wave coming in and being reflected back. You can create devices that do this. And what's more, it actually has broadband performance. So when you do the simulations of this, you can show that this operates over a very wide range of frequencies. This is slightly too high in frequency for what you would be interested in geophysics, but nonetheless, it does demonstrate the concept. So if I return back to Philippe Roux and his colleagues in Grenoble, these are actually experimental field results from the initial experiments they did before they got the ANR grant. The more recent experiments and field trials are much more impressive than this. But the proof of concept, which was used in order to go and make a grant proposal and get some funding, simply demonstrated that we would predict band gaps, we would do simulations, and the waves through the forest would behave as predicted. Now you might say, of course, that it all sounds very fanciful. How do you know it works? So I was giving a talk in front of not a geophysics audience, but a mechanical engineering conference, and a professor came up at the end who said, "I've got a lab. I'm going to build this. I can't do it. I can't build you your forest, but if you scale it down in size and up in frequency, I'll build it out of metal." So we said, "Okay, well let's do an ultrasonics experiment." As far as one's concerned in terms of elastic waves, a metal is not a soil, but nonetheless, if one's prepared to live with linear elastic waves, it's going to satisfy the same governing equations. So this is now, it's about the size of this microphone in size, and it's got very, very small, a couple of millimeters high. He builds a little wedge, uses what in English we would call a milling machine. It's an automatic machine, and then this is not done at 10 hertz. This is done at 400 kilohertz. This is ultrasonics, and they do the experiment. And this is the theory for their experiment. It's basically scaled up in frequency, scaled down in size. And the experimental results are at the bottom, going from short to high. They fire the waves in. They enter the wedge. They get reflected back. He sends in a broadband, and you can put it through a Fourier spectrum. You can look at the Fourier spectra. You can see that it turns around where you say it will, and it does everything you say. You can see the mode conversion where you send the wave in, it gets sent down. Because he has a finite sized block, he can use a laser on the bottom to measure the displacements. It works exactly as predicted. So now let's turn, so that's sort of surface mode conversion. So that's attempting to fire waves in, put a device on the surface, or maybe inside the surface. You can put their resonators inside the surface if you don't like the look of them. Now let's talk about trying to design lenses on the surface of the Earth. So how would this work, right? So what we want to do, I'm going to talk about Luneberg lenses. So a Luneberg lens, it looks like this. It's a circle, basically. You change the material properties in the circle in a supposedly clever way. You use homogenization theory to find out what the effective refractive index is inside that circle. You fire a wave at it, and if you get it right, the wave all gets concentrated at the far end. Now, if you put 4 of them in the arrangement there, the wave comes in, goes to the point at the end, jumps into the next lens, and then propagates off. Now, what that means is at the place where the 4 of them are meeting, right in the center there will be no wave, there'll be no energy there. So you can make a place which would be still. You can design these 4 lenses, so the bit in the middle is still. So then, knowing that we could do this conceptually, then we attempted to design this. So we used realistic parameters in terms of soil and concrete and so on to design that. And then this is the theory, this is the homogenization. These are snapshots when you fire the waves in on the left-hand side. We've put a little building here. We use a seismological code called SpecFM. So we use a code which is well known in geophysics. We fire the wave in and we measure the vertical displacement at the top of the building. And we do the same where it's supposedly protected. You can see the protected building does get a bit of vibration because this is actually an approximation. This isn't quite as simple as electromagnetism. It's not quite, you can't make a perfect lens on the surface, but you can do pretty well. And if you look at the energy that the surface is feeling when you fire waves at it, on the left-hand side, you wouldn't necessarily want to be in that building. On the right-hand side, where the lenses have been, it's doing as designed. The wave is jumping from one lens to the other, leaving the center relatively unscathed. You can look at the power spectrum of the building or the object in the middle, and you can ask, how many dB is it reduced by? And in the critical range of frequencies between 1 and 10 hertz, around 5 hertz, which is probably around where you'd like to protect the object, it's dropping by about 10 or 15 dB, which is quite significant. I should have said that there is of course something one should be very careful of with this arrangement. If you fire the wave in at 45 degrees, the wave it'll do exactly as predicted. It'll jump straight to the other end of the lens, concentrate all the energy, but of course that's going to concentrate the energy exactly at your house. So please do not go and build this. This is a proof of concept. This is just showing that one can conceptually do this sort of thing. So that's a kind of health warning. The final thing I'm going to talk about are seismic shields. I don't know how I'm running on time, but 10 minutes? So this is what's called phononic crystals. So in this case, one could imagine that you have a layer of soil and then a solid bedrock. Now, what can we do to try to create a barrier so waves are fired at this object and then reflected back? How would this work? Well, let's take our building and let's surround it by an arrangement of pillars. These are now in the ground, and you drill all the way down and you connect to the bedrock. So I'm taking concrete pillars down to the bedrock, clamping them down there. And we're going to arrange them in a square or a hexagon or some periodic pattern. And indeed, Stefan and Sebastian and their colleagues have done some experiments along these sorts of lines. So this isn't. I'm rather conscious that as a physicist mathematician coming and talking in geophysics, that it may all look as if this is all rather conceptual and not practical. But people are taking these ideas up and attempting to do things with them. Now this picture shows frequency versus wave number again. But the key thing to notice is that if you take a finite slab of material and you drill holes into it and you clamp it at the bottom really tight, you can get a situation where you get something called a zero frequency band gap. This means that very, very long waves and very, very low frequencies will not propagate through that crystal if it was infinitely large. Now, obviously, we're going to truncate it and make it a bit smaller, but if that crystal was infinitely large, waves at very, very low frequencies would not propagate through it. Now, in the most extreme cases, you just take a slab of material and you clamp it at the bottom. It does actually have a zero frequency band gap, but it's so small that it's actually useless. But if you design things where you either shape the column or the size of the column or the arrangement, you can make that zero frequency band gap really pretty big. So you can design things so that when you fired waves at this crystal, all of the energy, no waves would propagate through it, all the energy would come back. Obviously, once again, there's a health warning here. You'd probably want to be careful if you put it around a building. If you start firing waves or there are waves incident on it, the reflected waves might land up on someone else's doorstep, literally. Once again, this sort of thing has been built. These are experiments by a group of physicists. Instead of doing the half space, they're doing very, very thin plates. Once again, They build it, they fire waves at it, they measure the surface displacements with lasers. Once again, this concept all works. On the left-hand side are some of their experiments. On the right-hand side are some numerics. What we predict is exactly what they see. Once again, this is because they're physicists. These are at frequencies that are dissimilar to those that you would care about. But it's the concept that matters. The concept works. So I'm sorry I skipped through a few slides. You're standing there, and I realize my time must be up. So I've tried to illustrate 3 different designs for mitigating seismic and ground vibration. They're quite different, I think, probably from the designs that you may have seen. So much of this work's done with engineers, physicists. Some of them's done with MENAR, other companies, lots of academic papers. And basically, I hope you found this interesting. And hopefully you've seen that when you go to conferences, there's some side session on seismic metamaterials. You'll feel emboldened to go, and you'll actually know a little bit about it, which would hopefully be nice.
Thank you so much. Une présentation brillante parce qu'elle nous permet d'avoir une synthèse en une fois finalement de différents niveaux de longueur d'onde, bien sûr. Vous avez pu voir l'application sur le cas des ondes sismiques. Richard l'a clairement montré. Si effectivement, ne pas hésiter à poser vos questions en français ou en anglais, comme vous le souhaitez, par rapport à cette dynamique des matériaux structurés d'une certaine façon.
Do you think that if you had to protect a building from blasting technique, could you use what you have approached there?
By blasting technique, you mean a nearby demolition or in some explosion?
Yeah, I'm blasting. I have a quarry not far from the building, and I want to avoid the waves to come to the building and avoid any movement within the building.
I think this. We would have to look at the frequency spectra of your signal, but I suspect I would like to think that these ideas would be of some use. I can't promise that you would get massive reduction, but I think that one could try to look at the problem that you're talking about and design. We would see what frequency you were operating at, and then try one of these three, and see which would work best. I can't promise, but
It's a hope.
Yes, yeah. I think until someone builds, when someone is brave enough to build one of these, and they can show it works, then I think people will try them all over the place. That's what happened in physics when people started doing this 20 years ago. Sorry, I can see someone else.
Thank you for the explanation. I have not understood if the system is very effective for vertical incident waves.
So I concentrated mainly on Rayleigh waves, partly because of time. But we have, by vertical incident waves, sorry, do you mean what I would call SH waves, love waves, or you mean waves from the bottom? So if what I've shown is designed for surface waves. If your signal is directly underneath and I'm protecting the surface, it's not going to do anything to help that.
Do you think some system exists?
So if that were the case, then I would start looking at things to do with foundations. Foundation protection would be what I would do.
Une autre question? Oui, Jean-François?
Thank you for this very interesting, very nice presentation. I would like to know how it could work in the case of attenuating media.
Oh yeah, that's a very good question. So we're actually looking at that now. We're looking at at the moment this is all perfect. There's no viscoelasticity, there's no plasticity, there's none of this. This is all perfect linear elasticity. And that linear elasticity, it has its deficiencies. It's low amplitude waves effectively. It's linear. There's no attenuation. There's none of the viscous plasticity. None of those sorts of effects. So yes, we are currently looking into this into pretty much exactly that actually. What do you do if you have nonlinear resonators? What do you do if you have damping? How could you take the energy out of this system since we know we've designed it, we design it so that we can take the energy where we want. Does that mean that we can then extract energy from this system? How would you do this? And does that affect the signal and the reflections that you would have got? So these are all good questions, to which I don't know the exact answers.
Merci beaucoup. Une dernière question pour Richard. Oui, j'arrive.
Bon, désolé, je vais poser la question en français. Donc, j'ai pas
C'est
bien
un
compris.
challenge.
J'ai pas bien compris quelle application concrète est pressentie pour système et quel intérêt il a comparé au système d'isolateur dont on dispose actuellement pour isoler le bâtiment.
I think you might have to, it was a bit quick for me.
Yes, which are the difference between we can observe with this classic system like insulator, seismic insulator inside the building itself, on what we can bring with this type of element in the soil. This is the difference between those both type of equipments.
So by the classical thing, you mean basically you create a trench, fill it with concrete. I would say what you would win is that these would be much cheaper to make because you wouldn't need to use, it would not be so disruptive. It would be cheaper, easier, I would hope more effective. The trouble is, by more effective, it's always, in English I would say, how long is a piece of string? If you are prepared to build something massive, it will be perfectly effective. It's very hard to compare like with like. One can ask, can you get a performance? I guess the real question would be, I want to lose 10 decibels. What do you have to do traditionally to lose 10 decibels? What do I have to do to lose 10 decibels? How do those two systems compare in terms of cost, efficiency, and a variety of other questions? I think both systems would get, that loss, but then I would question, if you did it traditionally, how expensive it would be and how disruptive it would be to build. I hope that's a fair answer. I haven't tried to dodge the question, I think.
Yes. Yes, this is a modification of the signal itself compared to the passive device inside the building, like insulator or something like this. Here, with this equipment, we try to modify the kinematic effect itself, And
I see. Sorry, I misunderstood the question. The question is, I take my building, I put resonators, I put a nice big swimming pool at the top. I do something to change the frequencies of my building so that my building does not vibrate at the frequencies where I think an earthquake will be coming. This is a different idea. This is an idea of trying to change the soil so that nothing ever gets to the building. How would they compare? I'm not entirely sure. But except once again in cost and scale and all those other things. Sorry.
It's okay. Thank you very much. Last question.
Is there any
Yes.
application in the maritime environment against big waves?
Oh yeah, so there are people looking into this. So this subject has become very popular, sort of fashionable probably. Certainly in electromagnetism, this, when it was developed, it basically started in 2000. There was an explosion of activity. And so various people from other wave fields have looked at it and said, I would like to use this idea in my field. And so there are people who do water waves who are also looking at whether one would call them cloaking, beach defenses, these sorts of things, trying to use typically the ideas from phononic crystals, typically the last idea I presented. So there are people who work on this. I'm not exactly in that field, so I'm not sure I can speak on their behalf. So.
Thank you so much, Richard. We can thanks again our speaker. Thank you.